Let's see some interesting examples of linear systems of equations, which have to do with applications to engineering or to physics, and that they will serve to motivate us, and give us an idea of the importance of algebra in the professional practice, and in the practice of daily life. The example that we are going to try is the example of a water supply system, which can also be used for the system of a transport network, or a system of internet-type communications, but there are many applications that would be equivalent. So, let's start with this very simple model, where we want to see a network of water supply. In any network of water supply there are a series of pipes, which are represented by the black segments that appear there, a series of nodes, that are the circles that appear in yellow color, and are elements by which we are going to be able to put or consume water. The deposits could be joined to the circles, and the pipes join nodes with others nodes. In this case, we have 4 nodes and we have 5 pipes. Let's assume we're getting water through the nodes, and let's call F to the flows that we are entering or extracting from each of the nodes. You have to understand that, as the arrows go towards within the system, we are assuming that we are inputting water. To differentiate the water that comes out from that entering water, we use the signs. When the sign is negative, it means that the arrow goes in the contrary direction. So do not be concerned, in principle, by the sign criterion that we use. Analogously, in each pipeline we are going to suppose that water circulates in the directions given by the arrows. We should not worry about its meaning, because if at the end the water circulates in the contrary direction, what will happen is that a minus sign will appear, which will change it, and nothing more. So, in principle, we have to decide, in each of the nodes, what happens, from the exterior point of view. If water is consumed or water is supplied, to put an arrow in the sense that we want, and, in the pipes we put a series of arrows. We have to put, also, some names at the flow rates that they enter from outside. In this case we have used the letter F, and since there are 4 nodes where you can enter or extract the flow from the outside, they are F1, F2, F3 and F4. Analogously, to the variables we give them a name. We have to name all the pipes, and we've given you in this what we have done, has been to indicate from where to where the pipe goes, in the direction of the chosen sense. So, x12, means that it goes from node 1, to node 2, x24, goes from node 2, to node 4, and x34, goes from node 3, to node 4. We have water circulating through that supply network, and what we have to do is to get some equations that must hold. The equations that have to be met are the flow balances. It is evident that what enters a node and what comes out has to be the same, if not, we would have a system in which the water comes from nowhere. Therefore, what we are going to do is to establish as many equations as nodes. In this case there are 4 nodes, then we have 4 equations. For example, in node 1 if we observe it, the F1 appears, x12, x14, and x13 appears too. So, what we have to establish is that the amount of water that enters, equals the amount that leaves the node. In this case we have that F1 is what comes in, and what comes out is x12, x13, x14, then the equation is F1 equal to x12 plus x13 plus x14. In node 2, we enter F2, and x12, and out, x24. Then, we could put what comes in equal to what comes out, or we can place, because it will interest us, everything external, all F, on one side, on a member of the equation, and all the x, in the other. Here what enters is x12 plus F2, and if the x12 is moved to the other member, changed sign, it would be that F2 plus x12, and what comes out is x24, which is the equation we want. But nevertheless, as the x we want is on this side, we had to change the sign, and it appears in this way. In the case of node 3, we have that flows that enter are f3, and x13, and what comes out is x34. So, if the x13, from here in the equation, we move it to the other member, we have f3 plus x13, which is what enters is equal to what comes out, that is x34. We have arranged the x on this side, and the f on the other side, because we are interested in doing that. Finally, in node 4 we enter everything, enter f4 x14 x24 and x34. Then it would be, what comes in, which is the sum of everything, equal to what comes out, which is 0. Then we move the x, changing their sign, with the minus sign, to the other member, and we have this equation. These four equations, what they represent are flow balances in each node, and this produces an equation per node. This is the system we want to solve. Since f1, f2, f3, f4, will be, at least 1, different from 0, we are in front of a complete system of equations. We are therefore faced with a problem of a complete system of equations. First, let's study its compatibility, that is, what conditions have to be fulfilled so that this system be compatible, and the conditions have to come in function of f1, f2, f3, f4, that is, what conditions must the f satisfy for the system to be compatible. Let's see what was done to solve the compatibility problem. The vector of independent terms, that is, f1, f2, f3, f4, should belong to the subspace generated by the column vectors of the coefficients. Then here we have the system, and let's do that. For this, you have to obtain the subspace orthogonal to the subspace generated by the column vectors. The first column vector a1, is formed by the coefficients of x12, which are 1 minus 1 0 0, and it is the vector a1, which we introduce in the algorithm. We add the unit matrix, we calculate the scalar products, and we pivot. The next column vector a2, is formed by the coefficients of x13, which is 1 0 minus 1 0, which is what we enter in iteration 2, as you can see. We calculate the scalar products and pivot. In iteration 3, we have the vector a3, of the coefficients of x14, which is 1 0 0 minus 1. Check in the equations that these are the ones that come from unknown x14. In iteration 4, we use the coefficients of x24. The first one does not have x24, then it gives 0, the second one 1, the third does not have, so it is 0, and the fourth is minus 1, and we pivot. At the end, we get the final table, which appears there, in which you can see that we have pivoted with the first three vectors, and you have to remove them. Then, the orthogonal subspace is generated by the vector 1 1 1 1. So, if we remember, the compatibility condition was that the scalar product of the independent terms vector multiplied by the subspace generators, it had to be 0, because they had to be orthogonal. So, we multiply the vector 1 1 1 1, by the vector f1 f2 f3 f4, which is the independent terms vector, and that gives f1, plus f2, plus f3, plus f4 equal to 0. Thus, the system is compatible if the sum of all vectors that enter the system is equal to 0. That is a very natural condition, because you have to keep in mind that in a system, the sum of the amount of water that enters, and the amount it comes out has to be 0. Then the sum of everything has to be 0, and this is the compatibility condition. We see that, from a mathematical point of view, we have a condition, which corresponds to the physical problem. We all understand that in a system, what comes in the system, has to be equal to what comes out, because if not, it would appear suddenly, something in the system by magic. Next, we will obtain its solution. We are going to solve the system of four equations, But now to f1, f2, f3, f4, let's give it a concrete value, and we are going to give them some values that meet the compatibility condition. Notice that 3 plus minus 1 plus minus 1 plus minus 1 is 0, that is, it fulfills the compatibility condition. If these values are altered and this condition does not hold, there would be nothing to do, because there would be no solution. Therefore, we have to put a concrete case. We put 3, there is a deposit in node 1, which gives us 3 flow units, and we take out from each of the other 3 nodes 1 unit of flow. To solve a complete system, what have to be done? We need to create a new fictitious variable, which has to take value 1. We have to multiply it by the independent terms and pass them to the other side, changed sign. So we get a homogeneous system, which had to solve it and then impose the condition that the new variable equals 1. So, the vectors that we have to use now to pivot are the row coefficients of the equations, taking into account that we move to the other member the independent terms, multiplied by the new unknown. Then, in the first equation, there would be 1 1 1 0 0 minus 3, because it has to pass with a changed sign. What is a1? What we enter in the first iteration, we calculate the scalar products, which in this case are free, because they are the same values, because we have the identity matrix, and we pivot. Next, we enter the vector in the second equation, which is minus 1 0 0 1 0 1, because the minus 1 passes changed sign, and there it is. We do the same in the third equation and in the fourth, which is the last one. In this, we have the vector 0 0 minus 1 minus 1 minus 1 1, which is a4, what appears in the iteration 4, and we cannot pivot. When we finish, we check that we have pivoted 3 times, then we have to remove the vectors that correspond to the pivoted ones, and thus, we obtain the orthogonal subspace that we are looking for solving the homogeneous system, that would be the one generated by the 3 vectors that have the v, the last 3. Finally, we have to impose the condition that the artificial variable is equal to 1, which forces the coefficient of the vector v3, which has 1 as its last component, which is what corresponds to the fictitious unknown, to be 1. Therefore, the solution is that the flow in the pipes 1 2, 1 3, 1 4, 2 4, and 34, as you can see there, it's the same to a particular solution, which is 1 1 1 0 0, plus a linear subspace, of dimension 2, which has as generators, which are base, the other 2 vectors in v1 and v2, which you can see. Then this is a very simple example. Here we interpret these vectors that have emerged. In the case of the particular solution it is very simple. The interpretation is very simple. If they enter 3 units by node 1 of the deposit, and we want to extract 1 from node 2, 1 from node 3, and 1 from node 4, we can enter those 3, and divert 1 through the pipeline 1 2, 1 through pipeline 1 4, and 1 through pipeline 1 3. Then, the other 2 pipes they would not carry flow and they would be 0. That is a particular solution. What does the vector 1 0 minus 1 1 0 represent? Well, it represents a unit flow that is circulating from node 1, to node 2, to node 4, and to node 1 again, giving there, and in the other pipes, those below, there is no flow. Note that for node x1 2, the rotation direction coincides, in node x2 4, matches, but for node x1 4, the direction of rotation is contrary to the vector direction. That's why, the third value in 1 0 minus 1 1 0, it is with minus sign, because it goes in the contrary direction. Analogously, the last vector above on the right, 0 1 minus 1 0 1, arises from considering that the flow is circulating, a flow cycling there, from node 1, to node 4, to node 3, and again to node 1, cycling, and that the rotation direction coincides with 3 4, and with 1 3, but it does not match with 1 4, so that we must change its sign. Next, there's a simpler example, that I want to leave it as an exercise, so that you work it as an example. It is this one you have here. You have 4 nodes, and there are only 3 pipes. Everything is explained here. I want that you analyze it, equation by equation, checking that there is indeed a balance, that what enters is equal to what comes out. Here, I want you to study the compatibility condition. What conditions have to held for the F values to be compatible? Find what the algorithm gives, and check that we get the same as before, that sum of the amount of water that enters the system globally and what comes out must be 0. Finally, I want you to obtain the solution for me. In this case, the solution is unique, since there is only one way to take the flow there. However, it is very good to have several degrees of freedom. Finally, we complicate a little more the example so that you do an extra effort. This is an extension of the previous example. You must recalculate the new system of equations. You must find the compatibility conditions and you will see that the same result appears again, that the overall balance has to be null. Finally, you must get the solution, but in this case there is a degree of freedom more. This gives a subspace of dimension 1, that you have in the solution. To this interesting example, other examples will follow.